Welcome dear students. Today in this class, this is the introductory class, I am going to talk about one important subject available in the BTech curriculum of uh, Tripura University, which is being implemented in our institution, that is digital system design. The course code of the subject is PCEC 502, and in this semester I will uh, take this subject for you. Like other course contents, this particular subject is also divided into 4 modules, and in the module 1 we have state machine. The name of the module is state machine, and the module starts with review of sequential circuits. So when we review the sequential circuit, we come across these topics. Initially, we will talk about introductory part of it. Thereafter, we will explore what are the different types of sequential circuit. We will explore latches and flip-flops as memory element, because sequential circuit do have memory element within them. Then in the memory element, basically two types. One is flip-flop, first one is latch and second one is flip-flop. So they have their own properties. So we will explore them. And in the flip-flop, the dominant part is the ACE triggered flip-flop. We will talk about them. We will talk about two important attributes of the flip-flops. One is called characteristic table, another one is called characteristic equation, and the flip-flop often require asynchronous input for certain asynchronous operations. So we will explore about them also in this lecture. Now each of this lecture is having a learning outcome. At the end of this lecture, a learner is expected to have differentiate the circuit types. Basically, the digital circuits are of two types. One is called combinational logic circuit, other one is called sequential logic circuit. So the learner will be able to segregate them, compare them. Also, they will be able to compare synchronous and asynchronous operation. What is the difference between a latch and flip-flop? The learner will be able to identify the differences. They can analyze the basic latch, how it works, how they can be used in a digital circuit. Then the next version of the memory element is the flip-flop, which is derived out of latches. So their operation, their timing analysis, because all these memory elements are revolve around a reference clock. So the timing aspect is very crucial when we design sequential circuits, especially high speed sequential circuit. So over there we will get to know what are the different parameters in terms of timing, and then the learners will be able to also identify the characteristic table, characteristic equation for all 4 types of flip-flops, that is D flip-flop, JK flip-flop, T flip-flop, and then SR flip-flop. Side by side, they will also get a very good understanding about the asynchronous inputs, that is preset and clear. First of all, we will talk about the sequential circuit. The basic composition of the sequential circuit is described by this figure, where we can see there is a combinational circuit and there is a memory element. Now, the essential thing of a sequential circuit is to have a memory element, at least one, it can be more than one, and there can be some combinational circuit, and the output of the sequential circuit is decided based on the present input applied over here, and then the the status stored in the memory element is feedback as another input, and these two actually decide what will be the output of the sequential circuit. So, uh, some examples are of sequential circuits are such as counters, shift registers, then a digital clock, memory devices, state machine, etc. Now, when we enter inside the sequential circuit, we find there are basically two types of sequential circuits available. As this diagram depicts that, one is called asynchronous sequential circuit and the other one is called synchronous sequential circuit. To understand the fundamental difference between them, let us focus on these two figure 2 and figure 3. First of all, let us see figure 3. Uh, Over here, these boxes represents flip-flop, and this is basically T flip-flop, and this is a 2-bit up counter whose nature is to count up. That means if it is in presently in 0, it will go to 1, it will go to 2, and this way it is forward counting, up counting. And as we can see over here, this is a age triggered flip flop from this triangle, and the clock signal, which is the very vital reference signal in sequential logic circuit, is being applied simultaneously to both the uh, flip flops. As we can note, the same clock signal is being applied to both the flip flops. So, this is the basic fundamental nature of a synchronous sequential circuit. But if we see the same thing in asynchronous up counter, we can see that the original clock signal is applied to one flip flop, but it is not applied to this one, this subsequent flip flop. Rather, its clock input has been derived from the complementary output of the first flip flop. So, in case of asynchronous circuits, asynchronous sequential circuits, the basic difference between these is that the clock signal is not applied parallelly or simultaneously to all the flip flops. Now, few attributes of asynchronous sequential circuit has been listed, and so is the case for synchronous sequential circuit. As we understood, asynchronous sequential circuit does not use a common clock signal. Then the state change occur as soon as the input change, because it is asynchronous to the clock. So, as a result, the output can change at any time. Then it is better, it may give better performance, but the problem is that it is relatively harder to design compared to sequential logic circuit. Now, synchronous sequential circuit, as we understood from that diagram, that it uses a common clock, then the state changes only when there is a edge in the clock signal. It can be a rising edge, it can be a falling edge, and they are easier to design, analyze and test. So, next we will discuss about the fundamental of the sequential circuit, that is basically a memory element, and a memory element, as we know, is responsible for storing one bit of information, that is a 0 or it can be a 1. So, when we talk about memory element, basically we find two types. The fundamental one is called latch and the derived one is called, the other type is called flip flop. So, latch has certain properties, they are level triggered devices. What does level trigger means? Let me try to explain with the help of a diagram here. So, this is the clock signal as we were referring in the previous slide. So, if if a sequential circuit is to be level triggered, then it will be active, the circuit will be active when the clock is in the logic high state or logic 1 state. During this time only the level triggered circuit, that is latch, will remain active, and when it is 0, this position is called 0 or low. During this time the clock will not, the latch will not work. This is the usual convention, but there are negative logics, we will explore them in due course of time. And But in case of flip flop, as we can see, they are age triggered. Age triggered means we can see there is a transition from 0 to 1. This is low to high or 0 to 1 we can say. So there is an age. This is called positive age triggering or rising age, and this is called negative age triggering or falling age. So a flip flop usually respond to either positive age or it respond to the negative age of the clock signal. So that's why they are called age triggered device. It will not respond simultaneously to both. We can design the flip flops in such a way that they will respond to only one type, either positive age or negative age, and their output changes only at a specific clock age as rising or falling age. And examples of such flip flops are SR flip flop, JK flip flop, D flip flop, T flip flop. Now we will explore the latches in details, how latches are made from the digital circuits, digital resources, especially from NOR gate and NAND gate. So this slide explains about the very fundamental logic circuit in sequential logic circuits, that is the latch. So which is capable of storing one bit of information, a 0 or a 1. It is a level sensitive device as has been discussed in the previous slide. So it is capable of storing one bit of data, and then it has feedback path. We will explore that because the gates that are used, NOR gate or NAND gate, that are used to construct a latch, actually we will see they are having feedback, and they are level triggered, and they are actually simpler than flip flop. Actually flip flop is the next version of the latch, and that has been reiterated over here because they are the building blocks for the flip flop and memory circuits. Now if we talk about SR latch, which is the very fundamental latch, we can see how it is constructed. This diagram, that is the figure 4, explains provides us a very clear view about the SR latch constructed using NOR gate. We know NAND gate and NOR gate are the universal gates. So the first NOR gate has been used. We can see that the output of the first gate is cross coupled and given as input to the second NOR gate, and then output of the second NOR gate is cross coupled and given as the input to the first NOR gate. And NOR gate has property, it is just opposite of OR gate. So OR gate, from the truth table, from our previous knowledge of digital electronics, we understand that OR gate output is 1 when it's any of the input is 1, and output is 0 when all the inputs are 0. So NOR will be having just reverse of that. So its output will be 1 when its all inputs are 0, and output will be 0 when any of the input is 1. So with this understanding, we proceed to understand the function of NOR latch, as the two inputs are called set reset. From the name itself, this is a set reset latch, and this is function table or truth table, as we can see. First, if we apply 1 to this one, where is that? S is over here. So if we apply a 1 and a 0 to this, as soon as a 1 is applied, so the output of this gate will become 0, and when this 0 is feedback to this input, so both the input 0, the output will become 1. So this is the state it is referring to over here. So Q is 1 and Q bar is 0, and this is called set condition of this latch. Now under that situation, if under this situation, if just a minute. Yeah. So, if we apply now a 0, rather 0 to both the inputs, then and let us assume that it was having a 1 and 0 at the output. So, then its state does not change. How? Let us see. So, both the inputs are 0, and since this was 1, so this will be feedback as 1. So, one of the input of this NOR gate is 1, which makes the output 0, and this 0 and this 0 will make the NOR gate output 1. So, Q is 1 and Q bar is 0. So, that means when we have applied this condition at the input, so output has not changed from its previous states. So, that is why this situation is called that no change or previous state of the NOR latch. So, similarly other operations are easily understood when we change the input, when we reverse the input as has been mentioned in this row. So, obviously the output condition will reverse, and again if we apply the no change condition at the input, so output will not change, and one of the input condition, that is 1 1. So, this is 1 and this is 1, which is prohibited in case of SR latch. So, we cannot apply. The reason is that it will violate the output conditions. You see, Q and Q bar, they are complementary to each other. So, when both the outputs are remaining in the same state, so that means they are violating the output condition. So, as a result, this is an invalid state. So, we should avoid appearing this condition at the input. So, this is about our NOR latch. Now, next again SR latch, but this time it has been constructed using NAND gate. Almost similar connections, but the only difference over here is that the inputs are actually inverted. Instead of set or reset, I would prefer to say this is S bar and R bar, and these inputs are actually S bar and R bar. So, that will give a very good understanding, and also similarity with the previous circuit that we have just discussed. And over here now, when S bar and R bar is there, we can draw S and R for this also, and we can add over here that just opposite of this, when S bar is 1, R bar is 0. So, obviously this will be 0 and this will be 1, and here it is 1 1 means it will be 0 0, 0 1 means 1 0, 1 1 means again 0 0, and this 0 0 means it is 1 1. So, now this is matching. If we see this 2 column and this 2 column, so then it is matching with the previous one, previous slide. As we can see, it is matching with the, it is exactly matching with the previous one. So, over here now we can see NAND gate has the basic truth table property, like it is opposite of the AND gate, and AND gate output is 1 only when all the inputs are 1, and if any of the input is 0, output will become 0. Now, NAND gate is just having the reverse operation. So, NAND gate output is 1 when any of the input is 0, and its output is 0 when all the inputs are 1. So, with this property in mind, if we apply different conditions at the input, we will find that the NAND gate latch is exactly following this function table. So, it is quite simple. So, that is why I am not going into further details. Now, we can see that this is also a SR latch, but it is having an enable input. So, this portion is our SR latch, as we have discussed in the immediate previous slide, and the truth table is also available, or the function table. Now, here we are adding one additional condition at the input, that is enable input. This is enable input, we are adding, this is additional. So, and to incorporate that, we need to add 2 NAND gates more in the basic SR latch. Now, we see when enable equal to 0, when enable equal to 0, so what will happen? Both these inputs will get a 0, and when NAND gate one input is 0, its output will become 1. So, its output will become 1. Both the NAND gates output will become 1. As a result, when suppose if it was initially 0 and it was 1, so then this 0 will be here and this 1 will be here. So, we can see that 1 and 1 will make its output 0, this 0 and 1 will make its output 1. So, that means the output condition of the this latch will not change when the enable input is 0. So, that means the latch is disable state. So, this latch will be in active state or in the enable state when the enable input is a 1. So, as soon as the enable input is 1, so it will receive 1. Now, based on what we have fed, whether we have fed a 1 over here, let us assume that we have fed an 1 over here and a 0 over here. So, in that case, see both the inputs are 1. So, this will make this 0 and one of the input is 0. So, that will make it 1. So, for SR latch, so this is 0 and this is 1 means now it will go to 1 and it will become 0. So, this is called the set condition of the SR latch with enable input. So, and other operations, when we change it from 1 to 0 and 0 to 1, so obviously the output condition will become reverse, which is called the reset condition. The most important thing over here is the enable input, which is the control input, which has to be in active state. Active state meaning here is that it should be in 1 condition. Then only the latch will be functional and it will work as a SR latch, else it will remain in this state and the flip flop output under any circumstances will not change. Now, we will talk about D latch. Here D stands for data or delay. So, it has got 2 inputs, one is enable input, another one is data input. On contrary to SR latch, which previously we have seen over there were 3 inputs, S, R and enable. Here it is having only 2 inputs. So, this is much simpler than the previous one and almost same type of operation. Here only thing is that if we see in terms of previous one, this was S and this was R. So, an inverter has been connected between the D input and the between the S and R input. So, that makes the difference. So, and that gives us the one input D, and enable obviously whatever has been discussed in the previous one. So, when enable is 0, it will not function, rather it will remain in the no change condition. It will remain in the no change condition, and when it is enable, so if D is 0, so that means Q will be equal to 0, and if D is 1, then Q will be equal to 1. So, whatever is the input in the D flip flop, its output will be same when the enable signal is active. Now, this explains the graphic symbol of latches because in circuit we use their symbol only. So, how do we represent these latches in our digital circuits? So, this is representing our SR latch. This is fundamental SR latch. This is our fundamental SR latch, and these are our complementary outputs. This is Q and this is Q bar. This is SR latch with active high inputs. That means it is made of NOR gates, and this is made of NAND gates. That's why there is a bubble. So that's why this name is S bar R bar. And one that we have discussed is the D latch with enable input is depicted by this particular symbol. Now we are now marching toward flip flop to explore. Before discussing the flip flop, let us try to clear our idea about the clock signal. Previously also we have discussed. So this is basically the clock signal, and here this state is called logic 0, this state is called logic 1, this is again logic 0, and these are called edges. So any digital circuit that responds to positive level, so they are called edge triggered, they are called level triggered, and any circuit that represents that respond to the positive edge of the clock, so they are called positive edge response or positive edge triggered, and the other one is the negative edge triggered. So a flip flop is basically edge triggered device. Now there is another type of because you see in flip latches there are certain issues, because the output abruptly changes whenever there is a change in the input. Many a time the output should be synchronized with the clock signal, but since provision of clock signal is not there in the latch, so how to tackle this issue? So for that the edge triggering concept has been developed, and apart from edge triggering there is another concept that is called master slave arrangement. So this picture figure 10 depicts a master slave D flip flop. Here we can see that this is one latch, this is one latch, this is called the master, and this is another latch, this is called the slave. Now the enable input of this is connected directly to the clock signal, and the enable input of the slave is connected to the inverted version of the clock signal. So as a result, what will happen is that when the master works, so that means when the master is active, the slave remains in sleep state, it remains inactive, because you see when it is 1, so obviously enable will get 1 of the master, but enable of the slave will get a 0. So as a result this will remain in the silent state, and when the high period is over of the clock, then the output, the slave actually becomes active, and whatever has been stored over here, this is passed here, and as a result the output is available. So this is how the latch is the complete combination of this master and slave is made to respond to only one instance of the clock. They will not respond to both, they will respond to only one, though master is updated during the positive edge only, positive level only, but the slave is updated and it will provide us the final output only at the negative level of the clock signal. Now edge triggered D flip flop. Now we have understood that in flip flop mostly they are edge triggered. Now how they are designed, how the edge triggering concept has been implemented at the circuit level, this figure explains that. So here this is basically a D flip flop and easy to understand. So we will continue our discussion. We will now see about how an age triggered D flip flop works. Over here in this figure, that is figure 11, it is basically a positive age triggered D flip flop. So this arrangement is actually made for the D flip flop to respond to the positive age of the clock. So that means the flip flop content will get updated based on the input that has been applied on the positive edge of the clock. So let us see how it works. So age triggered D flip flop uses 3 SR latches. As we can see, this is one flip flop, rather latch, this is another latch, and this is the third latch. So these two latches, the first two latches respond to the external data and clock inputs. As we can see that the clock input is connected to the both of them and D input is connected to the bottom latch, and the third latch which provides, that is this one, provides the output of the flip flop. So see, when clock is 0, let us assume that our clock is 0 at this moment of time. Let us assume clock is 0. So obviously that will feed 0 to both the inputs. So, and as soon as we know that the NAND gate, one of the input is 0, its output will be 1. So the output of both the NAND gates are 1. As a result, which are connected to the input of the output NAND latch. So over here these inputs also receive 1, and 1 in the NAND latch at S and R input actually makes the flip flop in the previous state condition. So whatever was its value Q and Q bar, that will not change. So when we have come across this, this is with clock equal to 0. So so S and R equal to 1. So as a result, there will be no change. Now when the clock is 1, when the clock is 1, when the clock is 1, so what will happen? This will feed this one and this one, and during this time, let us assume that D is at 0 as the case over here. So this 0 will make this 1. So when this is 1, this will be 1. So since the previous condition was 1, so this remains to be 1. So all the 3 inputs of this remains to be 1. So as a result, this will be now, this will be 0 now. Since all the 3 inputs of this NAND gate are 1, so the output of this NAND gate will be 0. So and here, since this is 1, this input is 1 and this is 1, so it will make this 0. So this 0 and this 1 will make it at 1. So S is at 1 and R is at 0. So this is actually the reset condition for this flip flop. So that means with D equal to 0 and clock equal to 1, this flip flop has gone to reset condition, as is the usual case. Now at this instant of time, if the value of D also changes, suppose it changes from 0 to 1, that will not is not going to affect, because you see this being 0, it will feed a 0 over here, and as a result, though this input has been changed, but its output of this NAND gate will remain at 1, and that will make the entire circuit to remain in the same state. So that means what? The output of the D flip flop is logged. log till when? Log till the clock changes its value. Clock presently at 1. So, to change the value it has to go to 0, and then again when it becomes 1, then only it will respond to the new input that has been fed to D flip flop. So, this is how the flip flop has been logged, or it is made to respond only to the positive edge of the clock. In similar manner, when again after a transition in the clock, when it is made 1 and the D is 1, we will, if we perform the same analysis, then we will find that the output of the flip flop, that is at q equal to it will become 1. So, during that time again if we try to change D to 0, it will not having any impact because it is log. So, this is how an edge triggered D flip flop works, and this is positive edge triggered flip flop. That means it will respond to only the positive edge of the clock. So, this is the symbol that are used for positive edge D flip flop, and this is the symbol of the negative edge triggered flip flop, D flip flop. The difference is that there is a presence of a bubble indicating that this is negative edge triggered. Now, my dear students, we need to understand there are certain timing requirement which I was talking about in the initial remark, because when we deal with sequential circuit, we need to keep this thing in our mind, so that the setup time and hold time criteria we do understand, because these are when we design a bigger circuit, this parameter we need to keep in our mind, so that the circuit that we design will give us the desired performance. If we violate these conditions, in that case, though we design the circuit, then the result may not be expected one, there may be glitches. So, the timing diagram explains the setup time and hold time. As you can see that we are applying, this is the clock signal, we are applying the clock signal. Here it is a positive edge appearing here. So, before the positive edge appears in the clock input, we need to make the data availability. You see, the data transition or data available at the data input has been made to stable from this point onward, so that it gets enough time during this period when the clock makes a positive transition to settle the input data condition. So, this is called the setup time, and again when the clock has arrived, thereafter also there will be a time gap that has to be maintained, so that the clock can read the input data comfortably, and that period is called hold period. So, this is very important. So, as the definition tells, the response time of the flip flop to input changes must be taken into consideration. So, what is the setup time? The length of time that data must stabilize before the clock transition. This is what the setup time, and hold time is the length of time that data must remain stable at the input pin after the active clock transition. So, there are some other flip flops. As we know, in the family of flip flop, we have JK flip flop, we have T flip flop, we have SR flip flop. So, a flip flop basically performs three major operations. One is setting its output to 1, okay. Then making the output to 0 is another operation. So, that is called reset condition, and then complementing its output. Complementing means if presently the output condition is at 0, then the next value will be at 1. So, basically and these two flip flops, JK and T flip flop, performs all these three operations, and as a result JK and T flip flop are popular in designing the counter circuits. So this is a JK flip flop, the internal logic diagram. It has been constructed using D flip flop, which we have discussed in the previous slides. Now this is basically the D flip flop, which will follow the truth table of a D flip flop, and with certain arrangements at the input, we can convert this flip flop into JK flip flop. So the equation that is governing, the Boolean expression that is governing this transformation is written over here, where D equal to J Q bar plus, that means this is OR, K bar Q. So how that has been implemented, as we can see, this is the Q input, Q output, and this is the Q bar output. So Q bar is ANDed with J input, and then Q is here ANDed with K bar. So here we are getting J Q bar, and here we are getting K bar Q, and when they are ORed through an two input OR gate, so we get this expression available here. Now with this circuit arrangement, the D flip flop will work as a JK flip flop. So what is the special property of the JK flip flop? JK flip flop will behave simply as SR flip flop. That means when its inputs J and K are 0 0, the output will remain in the previous state condition. When J equal to 0 and K equal to 1, its output will be in the reset condition. When J equal to 1 and K equal to 0, the output will be in the set condition. But the last condition, where we have seen in case of SR latch and corresponding SR flip flop, so the 1 1 condition is the forbidden condition. So that means forbidden condition, why it appeared, we already discussed, because the output condition Q and Q bar, which is supposed to be the complementary situation, but that is violated. So that's why that situation, that input condition is not used, and it is kept as forbidden condition in case of SR flip flop. Now that problem has been solved in JK flip flop, because in JK flip flop, when J and K, these two inputs are made equal to 1, the flip flop output is a valid output, and that is called a toggle condition. Toggle condition means if the previous state was a 0, then when you apply 1 and 1 at the J and K input, then it will make transition to the other state. If previous was 1, then the present will be 0, and if previous one 0, then after toggling it will become 1. So this is what has been discussed over here. So next we have T flip flop. Next we have T flip flop over here. So T is another very popular and flip flop used for making counters and most of the state machine over here. This is the symbol of the T flip flop, where this is positive age triggered, as the symbol signifies that. So over here the same D flip flop now has been modified to make it as a T flip flop. What is the modification? Here we can see this is the symbol of an XOR gate. The one input of the XOR gate is connected with the input to the flip flop. In the present case it is T, and the other input has been feedback from Q to this XOR gate input, and the Boolean expression for this is, as we can see, D equal to T XOR Q. So and the XOR expression, Boolean expression, we know in the expanded form it is T Q bar or T bar Q. So the T flip flop has the advantage that it is having one input, one data input and one clock input, unlike the JK flip flop. Here if we take a JK flip flop also, from there also we can make T flip flop. if we tie the J and K input together with a wire, so that then the common input will be referred as T flip flop, will be working as a T input, and that flip flop will work as a T flip flop. So, it will be here we will be either applying a 0 or we will be applying a 1. So, when it is applied a 0, it will remain in the same condition, that means there is no change, it will hold its previous value, and if it is applied with a 1, then it will toggle. So, that means its output will change from its previous value. Next, most important in this lecture is the characteristic table and characteristic equation of our flip flops. So, in this slide, I have arranged all the 4 flip flops different conditions, that is characteristic table and characteristic equation together. First, we will start discussion with the SR flip flop. So, SR flip flop, as we know that having 2 input, we will get 4 conditions, that is 0 0, 0 1, 1 0 and 1 1. So, Qt plus 1, that refers to the next state, and Qt is our present state. So, when we apply, when the flip flop is in present state, maybe 0 or maybe 1, that is referred as Qt over here. So, the next state, what will be the next state? So, that is referred as Qt plus 1. So, we can see that there is no change in the state. So, that is true for you see, that is, this condition is true for JK flip flop also, SR flip flop, and even for T flip flop. So, this is for all these 3 flip flop, the no change condition is applicable. Now, when this is the reset condition 0 and 1, so flip flop output will be reset, that is it will be 0. So, it is set condition, flip flop output will be 1, this is set condition, and as I have already told that in case of SR flip flop 1 1 condition is the forbidden condition or it is invalid condition, so it is not used. Now, this is called the characteristic table of the SR flip flop, and this is the equation which is called the characteristic equation. Characteristic equation basically relates the output of the flip flop with the input. So, here this is the output or the next state Qt plus 1, and which is governed by S plus R bar Q. So, this is the equation, and we have to meet this condition SR should be equal to 0, so that this invalid condition does not appear. So, this equation is called the characteristic equation for the SR flip flop. Next, we have the D flip flop. So, this is quite simple. If the D input is 0, output will be 0, that is the reset condition. If D input is 1, then the output will be 1, and that is the set condition. And it is having the most simplest characteristic equation. So, it is the next state of the flip flop directly equal to D. Then comes the characteristic table and equation for the JK flip flop. Already we have discussed about this condition. 0 1, it is the reset condition, 1 0, it is the set condition, same as SR flip flop. But 1 1 condition, as I have already told, which was an invalid condition in case of SR flip flop, now it is a valid condition, and this is representing the complement, that is the previous value was 0, the next value will be 1 and vice versa. And this is the characteristic equation of the SR flip flop. We need to remember this very important equation, Qt plus 1 equal to J Q bar or K bar Q. Then comes our fourth flip flop, that is T flip flop. It is also quite simple like our D flip flop. So, no change condition we have already discussed, and if it is 1, then it will just behave like this input condition of the JK flip-flop, that means output will complement. And this is the characteristic equation governing the input-output relation in case of T flip-flop. So, it is T XOR Q, which in expanded forms it is looking like this. So, this characteristic table and characteristic equation are extremely important to us when we design digital sequential circuits. Moving ahead, in the initial few minutes, I have discussed about asynchronous inputs in the flip-flop. So, what is the asynchronous input? See, when we start an operation, a flip-flop, a sequential circuit where there is a flip-flop. Now, when we power on, it is not, we cannot be sure that the flip-flop condition will be in a certain state. For example, we want the flip-flop condition stored should be 0 when we begin the operation, but when we power on the device, power on the circuit, we cannot ascertain that 100%. So, there is a dilemma that whether the flip-flop already is having stored a 0 or a 1. So, before we start an operation, we need to sure, or we have to ascertain that the output condition should be at 0 or should be at 1, and we should be able to dictate that. For that purpose, we need to keep provision for inputs which are not working with the clock, and they are called asynchronous inputs. So, like here preset and clear. So, as we can see here, preset and clear, these two are called asynchronous inputs. So, they do not work in synchronization with the clock. So, what advantage we get? So, whenever we power on, before the first clock is applied, using these two inputs, we can make sure that the flip-flop is in the desired state. It is, if we want a 0 to be stored, we can do that. If we want a 1 to be stored in the beginning of the operation, that also we can ascertain. So, how that has been incorporated in this S triggered D flip-flop, which we have discussed previously, is explained over here. You just follow the blue line over here if it is visible. So, this blue line, on the top it is preset bar and on the bottom it is clear bar. So, when preset is equal to 0, because bar means it is active low logic. So, during that time this will be 1. Obviously, we will not try to preset and clear simultaneously. So, let us assume that we want to preset. We want to preset means we want to make Q equal to 1 before the clock applied. So, what happened? This 0 will ensure that this will be 1, and most importantly this 0 will ensure that the Q output is 1, and during that time all these things will ensure that Q is equal to 0. So, before the operation we ensure that Q is at 1 and Q bar it at 0. Now, on the contrary, if we want clear situation to happen, that means the flip-flop output should remain at 0. For that purpose, we will apply a 0 over here and we will apply a 1 over here. So, this 0, like the previous one, it will make 1 over here, okay, and this 0 will make a 1 over here. When it is 1, so this complementary connection will ensure that the Q output is at 0. So, this is how the preset and clear inputs, which are called asynchronous inputs and very extremely important inputs, which sets the initial condition, or even when during a circuit operation, suppose a counter is progressing, we want to disable the counter or stop the counter from counting up to its maximum value. So, we need to reset the counter, or in certain conditions we have to start the counter from the middle, not always from the 0 position. So, during that time also the preset and clear helps us. So, dear students, we are toward the end of our lecture, the first lecture on this digital system design, and on module 1, where we are reviewing the sequential circuits, which most of us has read in the previous course. So, as a summary of the lecture, what we have understood over here, so we got a review of the sequential circuits, how the sequential circuit is defined, how they look like, what is the feedback path, what is the storage element, how the combinational and sequential is connected. We have come across uh, synchronous and asynchronous operation of the circuit. We have seen what is the fundamental difference between them. We have discussed about the latch and flip-flop, how a latch has been constructed using NAND gate or NOR gate, and then how that level triggered latch has been converted into flip-flop, then what is its age triggered operation. We have gone through all these details. Then the circuit implementation and related mathematics, details of the architecture, function table, characteristic equation, and timing requirement like setup and hold times of the flip flops we have come across. Then at the end we have come across the asynchronous input, where we have seen the impact of preset and clear, the concept of preset and clear side by side, how they help in designing an operation of a sequential circuit, especially the basic element, the flip flop. Thank you.